Today we will learn the sequential circuit part 6, counters, synchronous counters. So previous lecture I already teach you the asynchronous counters, all about the asynchronous counters. Now in this section I will go for the synchronous. The synchronous counters, mainly the mod n counter. So the steps involved in the design of the synchronous counter are listed below. From the word description of the problem, draw the state diagram which describes the operation of the counter. Actually, the counter will counts from where to where, when in which state to which state, that will be defined in the step 1. And then depending upon the states, then you should draw the state diagram. Then step 2, set the number of flip-flops depending upon the number of counting states in the counter, which is already shown in the state diagram, using the equation 2 to the power of n greater than equal to capital N greater than equal to 2 to the power of n minus 1, where n is the number of flip-flops required and n is the capital N is the number of states present in the counter, actually which is defined in capital N. So make the state table. The step 3, make the state table depending upon the state diagram. Check the same to ascertain whether it has any equivalent states. If there is any equivalent states, then merge it such that one of the equivalent states can be eliminated from the state table. Thus, in this step, the state table is modified in such a way that there is no redundant state should be there. Then step 4, decide the what type of flip-flop to be used in the counter design, and then set the excitation table of that flip-flop. The excitation table comes from the state table of that particular flip-flop. And then the step 5, draw the excitation maps for various excitation inputs of the flip-flops and merge it to the state table, which is made from the state diagram. Then step 6, simplify the excitation functions using Carnot map, where the present state outputs of the flip-flops are the input functions and the value in the Carnot map are the excitation inputs of the flip-flop, which are defined in the mapped excitation and state table. And when you will get the excitation expressions of the excitation inputs, then you will draw the schematic diagram of the counter. Diagram we will get the 00 to 01, 01 to 10, and then 10 to 11. So if the present state is 00, then the next state will be 01. When the 01 will be present state, the next state will be 10, and if 10 is the present state, then next state again the 00, which is described in the state table, the present state and the next state. So present state, the present states are defined as the q0 q1, small q0 q1, and the next state are defined as the capital q0 q1. So the present state is suppose 00, then the next state will be 01. If this is 01, then 10. If this is 10, then it will be again 00. And the 11 case, we don't, this is the don't care. Due to the mod 3 means it will count the 3 states. So 01, 10, 01, 00, 01, 00, 01, then 10, then 00 again. So from this, the step 3 is here. Step 4 is the mapping. So map to it or merge with the step 4 is the decide the what type of flip-flop is to be used in the counter design and set the excitation table of the flip-flop. Although any of the 4 flip-flops can be used, but the selection of the JK flip-flop will result in a simplified circuit for the synchronous counters due to its toggling operations. So the excitation table made from the state table of the JK flip-flop I already discussed in earlier lecture. So just go for this, the 0 to 0 change, 0 to 0 change, 0 to 0 change. This is 0 to 0 change, this is 0 to 0 change. So 0 is fixed here. So we can neglect the 0 1 or don't care it's K. So for this reason it is 0D. Okay. For 0 to 1 transition, 0 to 1 transition, the 1 is fixed. The 1 is fixed, 0 1 is don't care. So 1D. Okay. So from 1 to 1, from 1 to 1, so then it will be decided that 0 is fixed but J is don't care. So D0. 1 to 1 change, D0. Okay. And 1 to 0 change, 1 to 0 change, this 1 to 0 change, this. So from here we will get 1 to 1 and 0 1. So that means the K is 1 and J is don't care. So D1. Okay. So then the excitation table will be made after considering or set the excitation table of the JK U1. Okay, and put the value of the J1 K1 J0 K0 to the Carnot map and then get the like this. So simplify the excitation functions using the K-map where the present state outputs of the flip-flops are the input functions and the value of the K-map are the excitation inputs value of the flip-flop. So excitation value of the flip-flop. Suppose this is a J1. So J1 we will make it 0 0. So 0 0 is 0. 0 0 is 0. So 0 0 is 0. And then 0 1 is 1. So 0 1, so that is Q1 Q0 Q1 Q0 0 0 is 0. Okay, and 0 1 is 1, and now 1 0 is D, 1 0 is D, and 1 1 is D. So now this group will be met and we will get the J1 equal to Q0. So simply this using this technique we will get 4 inputs of the 2 flip-flops at J1, K1, J0 and K0. So then we will the expression of J1 is equal to Q0, K1 is equal to 1, J0 is equal to Q1 bar and K0 is equal to 1. So then we will make the circuit according to the expression. So J0 is connected to Q1 bar, okay, present state, and the J1 will be connected to Q0. So J1 will be connected to Q0 and K1 is connected to 5 volt 1, okay, VCC, and K0 is connected to 1, that is 5 volt VCC. Then we will get the mod 3 synchronous counter. Another example is suppose mod 6 up counter. So mod 6 means up counter, means this counter count 6 state upwardly. Okay, so 6 state means 0 1 2 3 4 5. Okay, so now 0 0 0 is the initial state, 0 is the initial state. So then count 0 1 2 3 4 5, then again go to 0. Okay, and this 6 signifies that mod n is equal to 6, so small n should be 3 according to this equation. 3, so 3 number of flip-flops are required. So if we take three flip-flops, then the state table will be like this: Q2, Q1, Q0, and the next state will be Q2, Q1 and Q0. And if we take the JK flip-flop, then that should be the input of the three flip-flops are J2, K2, J1, K1 and J0, K0. So here in the state table, the present state will be 0, 0, 0, then the next state will be 0, 0, 1 according to this state diagram, and then 0, 0, 1 will be the present state, so next state will be 2. If 2 will be the present state, then 3 will be the next state. If we come to the 3, then 4 will be the next state. 4 is now the present state, then 5 is the next state. Now 5 is the present state, then 0 will be the next state, because from 5 it will go again to the 0. And other two state will be the don't care. Okay, put these J2, K2, J1, K1 and J0, K0 values in the Carnot map, where the Carnot map variables are Q2, Q1 and Q0. Put the value of J2 in the Carnot map, then we will get the J2 expression for K2, J1, K1, J0, K0, like this. Okay, so Q0, Q1, Q2, Q2, Q1, Q0, put this value and then make the group and get the expression J2, K2, J1, K1, J0 and K0. If we get the value like this, then make the circuit appear. Here the J2 is Q1 and Q0 AND operation. Q1, Q0 AND. So put an AND gate, and the two input AND gate, the one input is Q1, one input is Q0. Okay, and then this is the J2. Okay, and for K2, this is the Q1, only Q0, K2. So K2 will be Q0. So only connected to the Q0. Okay, so simply for J1, K1, J0, K0, we make the additional combinational circuits. Okay, and we will get the output like this: Q0, Q1, Q2. Q2 is the MSB and Q0 will be the LSB. So then we will get, okay, that should be 1. So now there is a mistake, that should be 1. So now after getting the 9 in the present state, then the next state will be 0, and others, the non-BCD numbers in the present state, the next state will be don't care. Next state will be don't care. Okay, so now the step 3 is over. Step put the excitation table and merge it to the present state to the next state depending upon the excitation table of the JK flip-flop. This is the present state, this is the next state, this is the present state, this is the next state, this is the present state, this is the next state, this is the present state, this is the next state, and this will be the data at the excitation input. And then make the table like this, and then put it to the Carnot map, where the Carnot map input variables are Q3, Q2, Q1, Q0, and the value should be put here as J3, K3, J2, K2, J1, K1, J0, K0, and we will get the Carnot map like this and get the final expression for J3, K3, J2, K2, J1, K1, J0, K0, and make the circuit like this. Okay, so then we will get the BCD or decade or mod 10 up counter. Now this is a very interesting example that is mod 6 unit distance code or 3-bit gay code converter. Mod 6 means, before going to the mod 6, the meaning of unit distance code. That means the unit distance counters differ from the conventional any binary or decimal counters. In that case, only one bit changes in the counter output for every change in the clock input. Suppose that is the 3-bit, so that means 000, so then 1 bit position change, so that is 00 should be intact and 0 and 1, here this is the 1 bit position change. When now this 1 to 3 should be there, because this is 0 and 1 should be intact, 0 and 1 should be intact, and then 0 1. So in between mod 6 means it will count from 0 to 6, no, 0 to 5, and 3-bit means that will count from 0 to 7. 3-bit means 0 to 7, 7 is made by 3 bits. Okay, so but here we will take the only 1 bit position state change. Okay, so if the present state will be 0, then the next state will be 1, that is 0 0 0, next state will be 0 0 1. Now the 0 0 1 will be the present state, so we cannot make it 0 1 0, because if we take the next state at 0 1 0 here, then there is 2 bit position change, so we cannot consider it. Then the next number should be considered, so that is 3. So 0 0 1 and 0 1 1, so only this position will be changed. Again this 3 will be the present state. Then what happens? Then we will consider 2, 0 1 0 here. Clear? I repeat again. The number will be, the total number of states should be the 6 in between 0 to 7, and as well as consider the 1 bit position change. So for this reason this is called unit distance code or the gray code, because we know that in the gray code the only 1 bit position will be changed. So that is 0 1 1, then we will go to 2. If this is 0 1 0 2, then we will come, either this will be changed, either this will be changed. If this will be changed, then 3 is already there, so then we will come to this. Okay, so 1 1 0, so here this is 1 1 0. When 1 1 0 is come here, then we will get only either 1 1 1 or 1 1 1 or 1 0 0. Okay, so then if we will get then 1 0 0 due to the mod 6. So it will count mod 6, that means 6 state. So 0 1 2 3 4 5. So in between 0 to 5 we should consider 6 states. Okay, so here we will get the 4 only. So 0 1 3 2, then 6, okay, then 4. So 6 tens means 0 to 5. The number of the flip-flops required is 3. Then the operation by this equation. So here we will get this state table. Why we will not take in 111 here, 111 here? Because 111 is not 111 is not considered due to the 0 to 5 state is 0 to 5 state is not covered. So here we will take the 6. Okay, we will consider 0 to 7, no problem. Okay, so the 6 will come before the 7, so for this reason here 6 is considered. Okay, so if we get this 1110 and then we will get to 7, no problem, but then we should eliminate the 4, but 4 is coming before the 7, so for this reason 4 should be getting the priority. So for this reason here we will take the 4. Okay, so this is the, so depending upon the state table, then merge it to the excitation table. Here we will make for your easier practice. Here we'll use the JK flip-flop, T flip-flop and D flip-flop, and according to the excitation table, this is the D flip-flop excitation table, this is the JK flip-flop and this is the T flip-flop. Put it here and then random map for J2 K2 J1 and J0 K0. Also for T2, this is the T1, T2 T1 and T0. Again this will be the for D2 D1 and D0. I only circuit depending upon the J and get the expression of J2 K2 J1 K1 J0 K0 and make the circuit, and should draw the circuit yourself by using the D and the T expression. Okay, then you will get the final circuit by using D and T. You should practice it. Now the last part is the mod 8 up down counter. So this is very interesting. To design a mod 8 up down counter that has 8 state, so 0 to 7, the number of flip-flops required is 3. From the equation 2 to the power of n greater than equal to capital N less than equal to 2 to the power of n minus 1, here we choose the JK flip-flop. Then the state diagram. Here there is a control input that is called M, which is equal to up and down bar. Up and down bar, that is called M. So if M is equal to 1, then it will go for the up. M is equal to 1, then it will go for up, and if M is equal to 0, then it will go for down. Okay, so now this is the control input scenario. So if the M is equal to 1, then it will go to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, and then 7 to again 0 due to the mod 8. Okay, so there is another extra input is there, that is called control input M, and if it is M is equal to 0, then it will go for 0 to 7. Sorry, if it is M is equal to 0, then this is the down counter. Okay, down counter means 0 to 7, then 7 to 0, 7 to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1, 1 to 0, and then again 0 to 7. So here the present state is 0, next state is 7, then we will go for 1, 1 to 0, then we will go for 2, 2, 2 to 1, and then 3, 3 to 2, here 3 to 2, so then 4, 4 to 3, or then 5, 5 to 4, then 6, 6 to 5, then 7, 7 to 6. Okay, and then again 0, 0 to 1 for this one, where m is equal to 1. Here m is equal to 0, m is equal to 0, here m is equal to 1. Okay, so then for 1, then it will get to the up counter 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to again 0. This is a very simple state diagram, only the control input here. So if the up and down bar, that is equal to m is equal to 1, then we will get the up counter, it will count from 0 to 7, and for the down counter, when the m is equal to 0, it will count from 7 to 0. Okay, then put the excitation table and merge it to the state table for J2, K2, J1, K1, J0, K0. This is the J1, K1. This is the J0, K0. And then you will the final circuit of this. Okay. And this is the output waveform of a counter. I here describe the only up down, then we will clearly understand what is the up and what is the down. Now if this is the up, that means m is 1. If it is m is 1, so m is 1 means we will get up counter. Okay, so then we will get, this is the Q2 means QC, so QC means QC will be the MSB, QC will be the MSB. Okay, so now if we put it the up, m is equal to 1, then we will get 0, 0, 0, then 0, 1, 0, so that is 0, 1, that is 0, and that is 0, so we will get 0, 0, 1 here. This QC will be the MSB and QA will be the LSB. Okay, suppose this is a C, this is B, and this is A. So ABC, so that is the QC, this is the MSB, this is the LSB. So then we will get 0, 0, 1. Now here this is the 0, this is 1, this is 0, so that is 0, 1, 0. So at that point this is 0, this is 1, and this is 1, so that is 0, 1, 1, so this is 3. So now this is 1, this is 0, this is 0, so that means 4 here. Okay, so after counting the 4, when m is 0, so that means the down count starts. Down count start means here this is 1, this is 1, and this is 0. Okay, so that means very simple, that means it will count from 3, because very simple, when it is 0, this is the toggling case will be occur. Okay, so J1 K1 should be 1, so then toggling will be occur. So here the toggling will be there. So this is 0 0 to 1, this is 0, this is 0 to 1, and this is 1, then this is 0. For this reason we will get 0 1 1 here. Okay, so now then again this is for 0, so then again the toggling, this is the, then we will get this is 0. Okay, but here this QB is inactive, 0 1, so it holds the data, so that is 1, and then this will be holds the data, so then we will get 0 1 0. Now then again this will come to as the toggle 1. Now again this is 1, so QA is 1, QA is 1. Okay, so this is the 0, so this is the 0, so 1 0, so this is the 0. But if Q1 is QA will be the 0, QA will be the 0, this is the 1 1, the toggling, before it will be as 1, so then it will be 0 toggling state, and if this is 0 then this will be the 1, so then this will be the 1, so 0 plus 1, so 0 here, 1 here, then 1 here. Okay, but the next next pulse, okay, clock pulse. So then what happens, then this will be stored the data 0 1 and 1 1 again. So if it is 1 1 again, then it will be toggling 0 to 1, then 1 to 0, then 1 to 0. So now if QB is 0, QB is 0 here, QB is 0 here, and this will be 0, so this will be 0, and this is the 1, but this will be the 0, so 0 and 0, so this is inactive, so for this reason this is the 0. Okay, now again the next pulse will come, so it will be toggle 1 to 0, and then this will not be able to activate, so this will be 0, obviously this will not be activated, so this will be also 0. Again it will get 1, so then it will be again the up counter. Okay, so this is the operation of a up down counter mod 8. It will counts from 0 to 7 depending upon the control signal M, up down bar. Okay, thank you. So thank you. If there is any question, please ask me through my mail ID or through the WhatsApp. Thank you very much.